Hello ladies and gentlemen, hope everyone is doing well today. We're going to continue on with section 7.2, which is known as slope fields, and as I mentioned in the video from yesterday, these are just graphical representations of differential equations, and we can actually use these to our advantage in order to sketch out a family of solution curves for a particular differential equation. Now you may also read that slope fields can be classified as vector or directional fields, and all three essentially mean the same thing. So we're going to take a look to see how we can come up with these sketches without a graphing calculator, and then I'll also show you a nice shortcut related to Desmos for how we can get a general idea of what these solution curves may look like. Now you may remember back from your Algebra 1 classes, in case you didn't have a graphing calculator, you can come up with a table of values. And so here, because our differential equation only involves x, we're just going to choose specific inputs for x here. Usually it's a good idea to choose numbers between, say, -2 and 2, or whichever ones relate to the given graph for that example. Now if you plug in -2 into this equation here, this is going to give us a value for dy over dx. In turn, that's going to be a -8. And what this -8 actually represents, it's going to be the slope of a line that we illustrate at x is equal to -2. And that's the whole purpose behind these slope fields. Essentially, when you're plugging in values into your equation, you're just illustrating lines with a specific slope related to that equation here. So we're going to do that for all of these values for x. So if I plug in -1, that's going to be a -5. So my slope may look something like this. And it's okay if your lines aren't exact, as long as you get a general idea on the direction of it. You know, if it's negative, it's going to be pointing down to the left. I'm sorry, down to the right. And as you get higher in your negative values, they're going to be more vertical as a result. So if I plug in 0, I get -2. So this one's going to be oriented a little bit more counterclockwise. If I plug in 1, it's going to give me a slope of 1. So now I'm positive in this line over here. And if I plug in 2, that's going to give me 4. And so this line starts to turn a little bit more and more as a result. Now notice how there is no y variable in this case over here. So the slopes at these other points where the x values are still the same are going to be exactly the same. So I can still draw those same lines as I did for those first 5 points, just on the top and bottom of each other here. We will take a look at an example in which y is involved, and it's going to change the lines quite a bit. So they won't exactly mirror each other based on the initial points that you illustrate. Okay. Now, this is just a general outline for the slope field. If you wanted to sketch a specific solution curve, then what you'll have to do is actually integrate this differential equation here. So as we did yesterday, we just want to get the variables separated from each other, so we can multiply both sides by dx. Then from here, you can integrate both sides with their respective variable. So if you integrate dy by itself, you're bound to just get y back. If you integrate 3x, that's going to be 3x squared over 2 minus 2x plus c. And this c here, as we mentioned before, is a constant. In terms of differential equations, what this might represent is an initial condition. Because essentially with your differential equations, you are dealing with a rate of change over time. So when the time is equal to 0, you may have a particular c value to sketch a specific curve here. Now, how this relates to Desmos, if you think about this function here, right, it is the antiderivative of your differential equation. And at different values for c, as you can see here, it's just going to be a vertical transformation of your graphs. So that's something that you may have learned back in Algebra 1 or Algebra 2. And these vertical transformations, right, they actually relate over to different solution curves that you can illustrate for your slope field. So if I were to sketch the slope field, say, for when c is equal to 0, then I'm just connecting these lines over here. So that way I get the general shape of a parabola. This is when c is equal to 0. If I were to do the same, this time let's say that c is equal to 1, then that's just going to be a vertical transformation upwards. So this solution curve has an initial condition when c is equal to 1. So this gives you a good idea to see what types of solution curves that you may have. And the nice kind of key characteristic here is that the graphs are going to look very identical to each other when you just have these vertical transformations occurring between them. Now if we take a look at an example in which we have two variables involved, x and y, first thing that we may want to do is just get dy dx by itself, like they did in the last example. So I can add that second term over to the other side, so I get y dy over dx, and then if I divide both sides by y, this is going to give me 2x over y is equal to dy over dx. Okay, and so now from here we can just plug in values accordingly. Typically, if you have two variables to work with this time, we can still use the same sort of process as before. However, this time I'm just going to keep my x variable to be the same for these first 5 points. And that y is just going to vary by 1 each time. And then I'll do the same over here. This time actually I'll make this positive 1. Just so that way we can see what the right side of the graph will look like here. So that's going to be 1, 1, and then I'll do the same first 3 y points here. Okay, so if I plug in, say, a -2 and a -2 into this equation here, I'm going to get a -4 divided by a -2, so that's going to be a +2. So at that point, -2, -2, I have a slope of +2 over here. If I do -2, -1, that's going to be a +4. So this time, right, our slope is getting a little bit more vertical. If you plug in, say, y this time, notice when y is equal to 0, your slope does not exist. And whenever you have a slope that doesn't exist, you just have a vertical line to represent this scenario here. And now we're just working backwards, so we're going to get, let's see, a -2 divided by that. That's going to be a -4. So now my slope is pretty much reflective of this one here, so I expect the same sort of scenario to occur this time when y is equal to a +2 rather than -2. So this is going to be a -2 for our slope here. Okay. Now if I plug in, say, 1, -2, now I'm looking down at this point. That's going to be a 2 divided by -2, so that's going to be a -1. Okay, so my slope may look something like this. If, oh, I'm sorry, that should be a little bit lower. Okay, and there we go. Okay, so if I plug in, say, a +1 and a -1 into y over here, that's going to give me a -2, so this one's oriented a little bit more vertically now. And same situation, because we're dividing by 0, that means this slope in particular is not going to exist. Okay. Now, to kind of give us some more points to work with, let's say that we plug in 0 in for x. Now, no matter what value you plug in for y, as long as y is not equal to 0, these slopes are always going to be horizontal. Okay. And the same sort of thing happens on this side too when we were dealing with x was equal to 1. Notice how when these y values became negative, or I'm sorry, they became positive from a negative, then their slopes essentially switched in sign. So here I'm going to have a +2 for a slope and then a +1. And as you can probably imagine, this whole column here is going to reflect the same column here when x is equal to -1. So again, you can verify this using a table, but essentially these slopes between each other are going to switch in sign, with the exception when x is equal to, oh, I'm sorry, when y is equal to 0 here. So this is going to look like this, and same sort of situation occurs over on this left column here. So our graphs are going to look like this. Okay. You may find that your slope fields can be symmetric in this aspect, and that's really dependent upon the expression that you have for your differential equation. Now, if we were to integrate this, right, we're just going to cross multiply on both sides. Sorry about that. So that way we can get our variables by itself. So we get 2x dx is equal to y dy. Integrate both sides with their respective variables. And this in turn is going to give you just x squared over here. And we'll put the plus c. And when you integrate y squared, this is just going to be, I'm sorry, if you integrate just y, it's just going to be y squared over 2. And notice here, since you have a x and a y variable, it may be a good idea to actually move both variables to the same side of your equations, particularly when they're squared, because this is going to relate to a function that you learned back in analysis. So we have y squared over 2 when we subtracted it from both sides. We can also subtract this c over to the other side, so we get a negative c. Now, because c does represent a constant, you don't necessarily have to put a negative sign next to it. You can still keep it as just c, because again, c could represent a negative number, so there's no need to be redundant in putting a negative sign next to it. And if we want to clean this up a bit, we can multiply both of those sides by 2, so we get 2x squared minus y squared is again equal to c. And this is your general solution for the differential equation. And if you take a look at this on Desmos, right, when c is varying, notice how as it gets bigger and smaller, you just have hyperbolas or parabolas in these cases. And so that relates over to the sketches for your slope field of this particular differential equation. Okay, I won't lie to you, this topic is rather tedious. We will get some extra practice with it though on Wednesday. Your assignment for today is just to work on a couple more examples with sketching. There'll be some pretty rudimentary examples, and feel free to double check your graphs over on Desmos or through a graphing calculator. And as always, if you have any sort of questions, feel free to email me and I'll be sure to help as I can. Hope you guys have a great rest of the day.